Okay, let's get started. So, final exam is Tuesday, December 11th at 1 p.m. All of you should have received your project number 5s back. Again, the grades were very, very good. But there was two things I wanted to discuss regarding them. The first thing was, how do we measure how good a confidence interval is? And number one concern is the true confidence level. Now let's say that you had two different intervals. Let's say number 1 and number 2. So maybe a BCA interval, maybe a basic interval. And the true confidence level was 0.956 for number 1, 0.946 for number 2, and the goal was, let's say, 95% confidence. Which interval is better? And I'm sorry, this is the estimated true confidence level. And so there are, let's say, B equal 500 simulated data sets. Which interval is better? Excuse me? They're equally good because they're both within the expected range. Now, there's 2 points I want to make about this specifically. First of all, some of you were saying, because interval 1 has a higher level of confidence, that one's better. No. You're looking at how close is it to 95%. If you state 95%, you should have 95%. Just because you have maybe a 99.9999% true confidence level does not mean that that interval is better, even though it has a higher level of confidence. You're looking at how close it is to the stated confidence level. So, closeness to 0.95. Then the second thing is that you need to take into account the Monte Carlo variation that's going to occur here because we're only using 500 simulated data sets. Similar to what we did in Chapter 5, using a normal approximation to a binomial. One can find 0.95 plus or minus, we'll take the 0.995 quantile from a standard normal, times the square root, 0.95 is 0.05 all over 100, and you get an interval of 0.925 to 0.975. Very few students brought up the fact that we have Monte Carlo variation so that actually anything that's inside that range is, well, okay. So in this case, both of them are inside the range, so that's great. And the reason why that's so important is because if I were to go out and simulate another 500 data sets, maybe the next time that I simulate it, maybe now I got 0.946 here, 0.956 here. Well, they're both equally as good because they're within that range. So you have to take into account Monte Carlo variation. Sorry, I wanted to discuss this, but I forgot about it. Let me see if I can find it real quick. So the same idea is used with respect to hypothesis testing. Hypothesis testing, you want to make sure that you have a test that has the correct size. So if I say alpha is 0.05, I want to have tests that if you were to simulate 500 data sets, that on average that you're somewhere between would be 0.025 and 0.075 if you're using 500 simulated data sets. Now, obviously, if you use something larger than 500 simulated data sets, you're going to have a narrower range. And to give you a kind of a dramatic example of actually even a statistician who was unaware of this idea, back in 2000, a group of researchers wrote a paper on basically something that I had discussed in my dissertation, but they took a different viewpoint to it. I got it published in Biometrics. And they said that their method was better than this other method that was actually proposed by my advisor a few years ago, because their estimated sizes were closer to 0.05. So in particular, so the goal was 0.05. And they were getting sizes for their particular procedure, and they were looking at a variety of different settings of like 0.052, maybe 0.053, maybe 0.049. And they use 10,000 simulated data sets. My advisor used, I think it was like 1,000 simulated data sets. And he was getting 0.056, maybe 0.051, maybe 0.061. And these authors in their 2000 paper said, oh, their method's better because they're always closer to 0.05. Why is it closer to 0.05? Because we're using more simulated data sets and have a smaller margin of error. And so in 2001, I wrote a reader reaction paper to their paper. And they had a number of other things that they were doing that was good in the paper too. But in particular, in section 4, I discussed variability of empirical significance levels. And actually state what I just told you. You have to take into account the Monte Carlo variation. So, anyway. Yeah. So the great quote then is, their particular procedure, appears to provide better control than the far more complex and bootstrap procedure of my advisor, Tom Logan. That's what they stated in their paper. But all it may be due to is just simply not taking into account simulation variation. Yeah, just a little bit of a side story there. Any questions about true confidence levels and actually understanding, what you're looking for?
Why do you use Z of 0.995?
I just chose to be a little bit more accurate, I guess.
I was just curious.
Yeah, there was no particular reasons. We're just using a normal approximation to binomial. I mean, some people will just say, let's just stick a 3 there, or a 2. Okay. Then the second thing that I want to do is talk about how to compare performance of the different confidence intervals. All of you did a good job with the actual numerical calculations, but the comparison, I graded very lenient here. The comparison wasn't always as good as I would have hoped. In particular, it's not good to talk about the individual cases. So, some of you will say, okay, let's look at n equal 9. I'm going to discuss the performance just for n equal 9. I'm going to go to n equal 20 and discuss the performance for just n equal 20. But I guess it's okay to do that, but as long as at the very end you come back and you examine all of it all together. So for all the sample sizes that you look at, and come up with overall conclusions. Now, one way to do that is to take a look at some plots. So after I got done grading your projects on Tuesday night, probably about 11 o'clock, I decided to do some plots for the next hour and a half, 2 hours. And unfortunately, I didn't get to sleep until about 1 a.m. But I was just having so much fun plotting that I just couldn't stop. So I actually did run all the simulations myself. And everyone got exactly the same results as I did, except for a few students who just, when they constructed their simulated data sets, they constructed them in a slightly different manner. They had exactly the same data, but instead of, I'll just say they constructed it in a different manner. They ended up getting just about the same values that I did for the true confidence levels and expected lengths, but they were usually different. And so, well, anyway, so I did all the simulations myself before I even gave you the project. And so what I did here after I ended up grading the project, so I decided, well, how about if I just put everything together in a nice little Excel spreadsheet. You can download this now from the project's webpage. I put that out there on Wednesday morning. And the reason why I did this is because I wanted to do some plots so that I can do some overall comparisons. And so let's take a look at how I do some of these plots. My end goal is to do a plot like this that we saw in Chapter 5. Remember I said, oh, I did these in S+. And I said, you could do them in R, but it's just a little more complicated. Well, now I'm showing you how to do it. The code that I'm going to show you is actually on the project's website now. Let's see here. So first of all, everything was in an Excel spreadsheet, so I'm just going to simply read in these simulation results. And what I want to do is construct what are called trellis plots, or also called coplots. There's a number of ways to do them in R. I chose to use the lattice package. This is a little bit an older package, but I find it easier to work with. A lot of people now are going to using the ggplot2 package, and I haven't unfortunately had the time to learn it myself. So I'm going to use the lattice package. And one of the things I'm going to need for the plot is I need to know the actual sample sizes that are used for each of the simulations. So if I take out sample size from my set 1, you see all the sample sizes that were used. But I need to make it a categorical variable. I don't want numerical values to be listed there. And if you've never done this in R, it's actually fairly simple. Use the factor function. And now it's categorical. So the only thing that you see different is this right here. It tells you the levels of your factor. I'm going to pull those levels out by using the levels function. So you see, notice how there's quotes around them. And then put them in an object called plot.level so I can use them. Now, a basic version of one of these trellis plots is to use a function in lattice called dot-plot, where I'm going to use CI in my set 1. This is the confidence interval name. That's going to be in my y-axis. On my x-axis is going to be the coverage level with estimated true confidence level. So just emphasize this. Go over it kind of fast. So CI, different confidence interval method. Coverage, just another name for estimated true confidence level. Here's expected length. The distribution used, sample size. I'm going to condition on distribution name. So notice how I use a vertical line to be condition. Data is in set 1. For each combination of these guys here, I'm going to group by sample size. You'll see the effect of that on the plot. I'm going to put a simple legend on the plot that's on the right side, and it contains values that are plot.levels. X-axis label. Layout is how I want my panels of my trellis plot to be arranged. Number of columns is 1, number of rows is 5. Notice columns comes before rows. So let's do this. And here's my plot. Confidence interval method, estimated true confidence level down here. What that groups argument allowed me to do was plot multiple sample sizes, the actual estimated confidence levels for each line in my dot plot. The colors correspond to the different sample sizes. Now, ideally, what I would like to be able to do here is actually use different plotting points so you can see it better. Also, to put a line at 0.95 for my estimated true confidence level, because that's the goal. If you want to do that, you have to get a little more complicated. Here's how to do it. And this basically will reproduce the kinds of plots that I had done in Chapter 5. So dot plot again. Same setup. I'm going to, since I have a little bit more complicated plot, I can't use this simple key function to do a legend. Instead, I have to do the following. I create a list, and inside the list you have a variety of arguments that you can put. space, right. I'm going on the right side of my plot. What points do I want to actually show on my plot? I'm going to use plotting characters 1 through 4, the following colors. The text I want actually listed next to each point is in plot.levels. Now, I need to be more specific about how each panel, just so that you remember what I mean by panel. This is a panel, this is a panel, this is a panel, controls plot terminology. I need to be more specific about these panels. So, I create a function where I pass in what goes on the x-axis, what goes in on the y-axis. I put some grid lines. Horizontal grid, -1. What that simply means is by default, I want these grid lines to be corresponding to what's actually being plotted. Next, v equals 0, that means no vertical grid lines. Line type equal dotted, line width 1, color light gray. Then I plot vertical lines at 0.95 so that I can get basically a line that goes up here. But also to emphasize that margin of error, you could say, that simulation variability, I'm also going to draw lines at 0.925 and 0.975 as well. Finally, this panel.xy plot says let's plot what's on the x-axis, y-axis. To get the color correct for the corresponding sample sizes, notice how the data is arranged here. Notice how the first 6 is one sample size, the next 6 is another sample size, and so on. So what I'm going to do is simply create a vector that has, let's say, green for the first 6 elements, red for the next 6 elements, and so on. And actually, I use a slightly different ordering of the colors, but you get the idea. I also do a very similar thing with the plotting character, and everything else is the same as before, so that we'll get this nice plot here. Here's a PDF of it. It's a little bit bigger. Okay. Let's talk about the findings here. Let's begin by looking at the student ties. And actually, I'm going to mark on this plot, so I'm going to bring this into a different software package, this PDF. Sorry. Too many files open. Let's see. It's not very difficult to open. There we go. Is that big enough, or do you need me to blow it up at all? Okay. So on the y-axis you see the confidence interval method. The x-axis you see estimated true confidence interval. You can see this is the goal, the solid line. Here's my margin of error. It's not showing up as well on this projector, but if you actually look at the PDF on the project's website, it looks a little bit better. And let's take a look at the first one that you did, the normal distribution. Let's look at this one. As you found out, both the normal base and the student ties interval both did well with respect to the confidence level. I'm not going to talk about expected length right now. But both did well there. And this is to be expected for the normal base, because after all, you're using the right assumptions, or using your data is coming from a normal distribution, which is the assumptions that this is derived under. But of course, the student ties has no assumptions at all in terms of the underlying distribution. Some other things to notice. Notice as your sample sizes are getting bigger. Notice the the ordering there of the symbols. As your sample sizes are getting bigger for all the methods, you're getting, excluding student types and normal base, you're getting closer and closer and closer to 0.95, which is what you would hope would happen for any kind of good interval. That as n goes to infinity, you are going to get the true confidence level. And it looks like they're headed that way. Slowly, after all, we used a sample size of 100. It still wasn't good enough. But they are getting there. Which one's the slowest, though? That's not. It's kind of interesting. So the Bootstrap ones are getting there faster. And remember what we learned about the Bootstrap intervals. Student ties and the BCA were the two best because they are getting to where they need to be faster. Obviously, student ties is already there. Well, look at this. BCA is always a little bit better than basic and percentile. It's getting there faster. And we see that. Just look at my notes, make sure I'm talking about what I want to do. Okay, so that's a normal distribution. Let's look at logistic now. Now remember, logistic is symmetric as well. Looks pretty much like a normal, has a little bit fatter tails, but it's really not that much different. In fact, if you were to do a histogram of a data set and plot and look at, let's say, symmetric mound shape, it's probably going to be very difficult to differentiate, a normal distribution histogram versus a logistic distribution histogram. Remember that. Okay, student types. All right, we're still in there. Now normal base. Uh-oh. Now I no longer have these underlying assumptions being satisfied here. And what's even worse is that notice, as my sample size is increasing, is it getting any better? No. That's not good. It's hovering around a little bit less than 0.9, about 0.87 maybe, right here. So even if you took a sample size of infinity, good, you're not going to get to 0.95. And this is especially important as if, you probably have seen this in a class before where you'll learn about a confidence interval for sigma squared. Which interval do you usually learn about? Normal base interval. Okay? And you're told, well, hopefully you're told, this assumes normality, so, you better check it. But what happens if you checked it with a histogram? Will you really be able to differentiate, as I said, logistic from a normal? No. Your performance is going to be really bad. Look at percentile, BCA, and basic. Again, as the sample size is increasing, it is getting to where it's supposed to be. It's not there, though. I'm sorry, look at the wrong one. It's not there quite yet, except for BCA, I guess, gets there. But it's getting close as n is about 100. So that's good. And again, notice how BCA seems to be getting there faster in terms of the n. Again, characteristic of what we learned before. Now let's look at another symmetric distribution, a uniform. Look at the normal base. Not good. Not good at all. And that's why, I was worried when some students were saying, oh, my true confidence level is higher, so it must be better. No. That's an example where it's not better. Student types, still right on the mark. But overall, the other intervals are doing better compared to the other two distributions. And in this nice little layout that I have here, you can see it all at once versus looking through some tables. But again, notice how the asymptotic is still kind of lagging behind all the other ones, even though it is eventually getting there. I think we see that too with logistic, even though I didn't mention it. Yeah, we see that also with the logistic. Now, what happens if I have some skewed distributions? Gamma. Studentize, not quite there, but still better than the rest, at least in terms of true confidence level. Look at normal base, it's getting worse to some respect as sample size is increasing. BCA of the other bootstrap intervals tends to do better. Asymptotic, still kind of lagging behind a little bit. Now, when you go to exponential, where you get even more skewed, that was kind of it. I found this kind of interesting there, although the intervals were wide. You look where studentize is. Normal base, you are actually getting worse as the sample size is getting bigger. I wouldn't be surprised if, with all the normal base investigations here, if you really crank up the sample size, it's going to get to one particular value, not equal to 0.95. It was actually, let's say, converge to it. So they won't all go all the way to 0, but will go to some place that's non-zero and not 0.95. BCA, better than basic and percentile. So anyway, it's interesting to see these results. That even with a sample size of 100, you may not do well. Nothing will do well. So, when I was looking at this then, I was thinking, okay, well, I have the opportunity to teach Stat 801 in the future, where this is a time where I would actually talk about confidence interval percentage score. Which would I teach? Well, do I want to do bootstrapping with my students? It might be a good recruitment tool for Stat 950. Then again, it might not be a good recruitment tool since those are non-statisticians who take that course. I don't know. I might just go with asymptotic because you can write it all out and just warn the students. You're going to need a large sample size to get this to work. So it's an interesting investigation there. It's a very simple parameter that we're dealing with here, but it's hard to capture with confidence. I did the same kinds of plots then with expected length. So you can see here on the x-axis I have the estimated expected length. And we can see the problems with the studentize interval for the very small sample sizes. Once you get up to 50 and 100, I'm not as concerned, but definitely with 9 and 20. And this is the characteristic that we've seen with these confidence intervals, that studentize will typically always be larger. Just so that we can get this on a more reasonable scale, I cut off the x-axis at in another plot to be about 20, and so that we can do some more comparisons here. And again, typically, as you would expect, as the sample size is increasing, you can see this visually. The intervals are getting smaller in length. We can see the asymptotic tends to always be the smallest. Not always, but most of the time always the smallest in length. Sure, you see normal base here is smaller than asymptotic at times, but I wouldn't even look at normal base because I know the assumptions behind it are incorrect. You notice, like, for example, here the BCA is wider. BCA is wider there. BCA is wider there. But then again, if you're comparing to basic, we know BCA is better than basic. We saw that with respect to true confidence intervals. The code to do these plots is in my program as well. So anyway, so what we just done here is, you can say, a little bit more of a thorough comparison across the sample sizes, and although you weren't able to do this, across the different distributions. When you do your dissertation or write a paper, you might have to, well, you're likely to have to do a simulation study under a number of different settings, and you can list all your results in the table or do a plot like this. Some other stuff that you can do with a plot like this, what I could do, if I looked at just symmetric distributions, I could organize them by kurtosis. So the smallest kurtosis first, next kurtosis, next kurtosis, and you can look for trends across the plots to see if there's something that's happening. As you get more fatter tails and distributions, do you have a trend amongst the true confidence levels? Also, you can organize then these non-symmetric distributions by skewness as well. As you get more skewed, what happens to the true confidence levels? Do you see a trend? That's what these plots really allow you to see versus just using a simple table. Okay, I've talked a lot, longer than I anticipated. I thought 15 minutes, it was 30 minutes. Are there any questions? Okay. Are there any questions about anything else before we get going with the main part of today's notes? Okay, let's move on. Okay, the last main section of Chapter 6 involves prediction errors with respect to regression models. And, you know, as you learned in another class before, a confidence interval would be for the expected value of y. What we often refer to as a prediction interval would be for y itself. Both are confidence intervals. It's just the terminology that has been developed over the years to help, I think, Stat 218 my students is let's call one a prediction interval, let's call one a confidence interval. I will call it a prediction interval here. Now, how would you do the bootstrapping then with respect to the confidence interval for the expected value of y? How would you do it? What's the first thing that you would do? Get resampled. And we talked about two different ways to get resampled. So implement one.
Get a resample and choose where you want it. What explanatory variables you want to.
Yeah. So choose what particular axis.
Calculate what your y is and your expected value.
So maybe what you're trying to say is get a y hat.
Right. Yeah.
For a particular x.
Right.
Repeat this a lot of times. Then with this, all these y hat stars you got, well, implement one of the confidence interval methods in the top. Okay. You should think about, too, what would you do for a studentized interval in this particular case? Well, we have standard formulas that you can use that are not based upon normal distribution approximations or normal distribution itself. We have standard formulas that you can use to get a standard error, and you can use that standard error, calculate for every single resample, and get your confidence interval. Now, what will we do for a prediction interval for y, though? Well, the nice thing about the expected value of y, it's a fixed constant. Y is not. It's a random variable. And it has an additional, then, source variability that you have to worry about, which is going to make finding these intervals a little bit more difficult. Okay, so in terms of the book's notation, y plus is what we're after. We want an interval for y plus. The plus doesn't mean we're adding over anything. It's just a way to differentiate this particular, let's say, observation from observations that would be in your normal data set. You know, some books will say y sub nu. Some books will say y sub h just to differentiate it. Our book uses y sub plus. This is actually going to be unknown because that's why we want to find a prediction interval for it. But what we do know is the corresponding x's. And we're going to put that in the vector called x plus. So what is y plus then in terms of our assumed model? Well, transpose of x plus times beta plus epsilon plus theta. That's what y plus would be. Or s, yes?
Resample goes y and x, not y and y.
We'll talk about resampling shortly. So this is y hat plus, the estimated value that you say a point estimate for y plus is just, as you would expect, x prime plus times beta hat. Now, what you're very interested in is how good would this point estimate be in predicting y? Well, how about we just simply take y hat plus minus y plus? If you knew y plus, you could do this. And that will be a measurement of your accuracy. The smaller it is, the more accurate. Larger in absolute value, let's say, the less accurate. How about we call that delta? Well, what does this mean, though, in terms of our model? Well, x prime times beta hat minus x prime times beta plus epsilon. And again, we don't know what beta is. We don't know what epsilon is. So could you actually, in application, calculate delta? No. But this is where, well, if somehow you knew what delta was, and you somehow knew the distribution then for delta, well, what would be then a corresponding interval? Let's say that delta is distributed, has some kind of distribution G. Then what you could do, just simply derive a little interval to y hat plus minus a particular quantile from G, and then take y hat plus a particular quantile from G as well, right? And we've done this all the way back in chapter 2.
Y hat plus the quantile from G. Too many pluses.
Well, I was worried about the plus there because really what you could do is you put a minus in there instead, and use, let's say, the upper quantile here, the lower quantile there. So I was worried about that plus and minus. I left off the plus. Anyway, but this just goes back to chapter 2. That's how you would find the interval if you knew the distribution of delta. We don't, and this is where the bootstrap comes in because we can estimate G. And so it's a great application now of the basics that we learned in chapter 2. What do we do then to estimate the distribution of G? Well, how about we form delta star. The y hat becomes a y hat star. The y here becomes a y hat. The epsilon becomes epsilon star. And so this is very, very, very similar to what we did in chapter 2. We don't know the distribution of t minus theta, so instead we estimate in that distribution the distribution of t star minus t. It's the same idea. Notice how this is now written in terms of our x's and our beta hats. So I have a star there. I do not have a star here. I do have a star there. Now, where does beta hat star and epsilon star come from? That's where you take your resamples and use those resamples to help calculate them. In particular, beta hat star. This is calculated as you would expect. Let's use model-based resampling here, and you'll see why it's better to use model-based and case-based resampling. Let's say I use model-based resampling. Then what I could do is estimate my model, my full model, get my mean adjusted modified residuals, R sub j minus R bars, resample from those Rj minus R bars to get my epsilon star, put that with my x times beta hat, and then get a y star from there. So that now for my same exact x's as were my original data set. Notice I'm not using x plus here. For the same x's, I have a corresponding y star. I can estimate my model, then to get a beta hat star. So that takes care of this part here. I have a way to get this beta hat star, then I multiply it by x plus. But what about this part here? Well, obviously this is just the observed x, well, I should say the observed. It's the beta hat from the observed data. Take it times your x plus. But what about this guy right here, this epsilon star? Well, this is where you need to take another resample to get it. So epsilon star plus is obtained from a separate resample from your mean adjusted modified residuals. So if you're interested in one particular x plus, let's say, you would need to do your resampling for beta hat star and then do a separate resampling to get one epsilon star in order to find this part here. So for every single resample, let me make sure I make sure this is clear. For r equal 1 capital R, you're going to be doing this. So get one resample size n. Do some erasing here, because my emphasis is clouding things up there in my notes. For one resample size n, you can calculate beta hat star. Then take another resample size 1 to get the epsilon star. Repeat this process capital R times. Is everyone clear about that? So essentially, if I have one x plus vector to worry about, I'm taking a resample size n plus 1. Let's say I had another x plus vector to worry about. I would take a resample size n plus 2. So I have, two sets of x pluses, but it's okay to use the same beta hat star. But because of this variability that we have left here, then I have to take then 2 more samples out of my modified mean adjusted modified residuals. You'll see an example of that coming up if it's not 100% clear. Now, the way that the book discusses it, they say you could take another resample size M. And I think it's actually, it kind of confuses matters by them doing it. I understand what they're trying to do is to be general. Let's say, perhaps you have M different prediction intervals that you want. Well, then that's where that M basically comes from. Okay. So now that we know how to do the resampling and how to calculate delta star, let's talk about prediction intervals. The standard prediction interval that you will learn about in a class like Stat 870 looks something like this. You take y hat plus your point estimator, subtract off 1 minus alpha quantile from a t distribution, take it times then the standard error that you need. The standard error looks like this. Hopefully that looks familiar. Your square root of your MSE times the square times then the square root of 1 plus your x plus vector times x prime x inverse times x plus. For emphasis, because this will be helpful later, you can also write this as s squared, all that stuff. Highlight it. All that stuff goes in there. It's obvious that occurs, but in some of the actual coding, we need to take advantage of that aspect. You'll see why as we go. Now, one little thing that's a little bit different in how I wrote this interval here is that typically instead of seeing a minus the alpha quantile from a t distribution, typically you see a plus t 1 minus alpha and minus p minus 1 to take advantage of the symmetric properties of the t distribution. But you can state this interval a little bit of a different way. Take your y hat plus, and then you have a quantile from the corresponding distribution of delta. So essentially, this is a quantile from a distribution, the distribution of delta, if you assume normality for your epsilons. But you might remember us, like, for example, in Chapter 5, this is how we wrote our initial interval out to emphasize what we're taking a quantile from. So what we could do then is use the bootstrap to estimate these two quantiles. So in other words, take I want you to remove m in here. Suppose m is equal to 1. I was trying to be general like the way they did it, but I guess I decided I think it's more confusing to do that, so I'm going to remove that. Take the r plus 1 times 1 minus alpha ordered value to estimate a sub 1 minus alpha. Take the r plus 1 times alpha ordered delta star to replace a tilde, a sub alpha, and that is your basic bootstrap confidence interval. Any questions? Now you might be thinking, okay, wait a second here. You know, when we discussed the basic bootstrap confidence interval, we always had 2t minus a particular quantile from the t star distribution. But you might remember that that actually came about, or hopefully you remember. If you don't remember, you need to know this for the final. This actually came about through doing this. Where this highlighted portion here is a quantile essentially from the distribution of what would be like this. Okay. Now, in our particular case, we cannot necessarily separate out the t from the t star here with respect to our delta star. So if we go back and look at delta star here, we can't do that kind of separation out. And so that's why I wrote the interval like this. Okay. What about a studentized interval? Well, let's again go back to how we would normally calculate our interval. Do some erasing again. Everything on the same page, but this doesn't happen. Just copy these. So on top here is our normal interval, and below here is now our studentized interval. So notice how I have y hat here. I have the s here, and basically what we've always talked about how is we're just replacing our normal distributional quantile with something that the bootstrap actually calculates. Well, what is this z star here? Well, it comes from the ordered values of the delta stars divided by the s stars, which is then the standard deviation of delta stars. So just to make sure it's clear, you're using the exact same formula for this s sub y that we saw here, but now you calculate it for every single resample. So that's why that's called S star. Okay, any questions before we get to an actual numerical example? Okay, so this is on page 72. The mammals data set. We have a sample size of 62, and we want to find prediction intervals for two x's. If you remember, x is body weight, y is the brain weight. And we want to find confidence intervals for two particular x's. And just to make things simple, we're going to choose X's that actually came from the original data set. And since now we know what these animals are, spell it, no? The 52.16 is a chimpanzee, and the 10.55, is that right, is a baboon. And that is extremely important for this example in terms of interpreting this problem. That's why I made sure I put that there. I hope all of you wrote that down. Anyway, these are observations 46 and 47 of the data set. There are a few errors in the book corresponding to this, and just be aware of that when you read it over the book. This actually corresponds to an example that was in section 11.6. Okay, so I read in my data. Here's my data. It's in the body data frame. It's in the boot package. I estimate my model. Remember, with this data, we are working with the natural log transformation of both y and x. Here's what my model looks like. And let me actually go over here to 10. I put the results from fitting the model in mod.fit. I put the results from summarizing the fit in mod.fit into sum.fit. And sum.fit gives me that summary. Now, for those of you who have not done confidence intervals and prediction intervals in R before for a regression model, this is how you can do it. First, I'm going to create a new data frame that contains my x values. In this case, body. Notice I use exactly the same word as it was in the original data frame. I say body equal 52.16, 10.55. And then I simply use the predict function. This is a generic function in R. It actually calls predict.lm as its method function. Object equal mod.fit. We put that there because this is where R gets all the necessary information about the model's fit. Then there's an argument called new data, and this is what you're making the predictions at for your x's. And it just so happens, because I made this simple, this data frame is called new data. se.fit equal true. This is going to print a particular standard error. You have to be careful about what the exact standard error is, though. See what I mean by that shortening. Interval equal prediction. If you had a confidence interval, you put confidence. Make sure you're familiar with how to do that. Level equal 0.95, 95% interval. So I'm going to put all the results into something called pred.newData, and this is what I get. Now remember that this is on the log scale. So log y hat is 5.1. The lower bound for the prediction interval is 3.7. Upper bound is 6.5. This is on the very bottom of page 674. Top of page 674. Go over there. This is what can be confusing. Notice R produces a list. The first component of the list is $fit. So if I only wanted this part here, I just say pred.newData $fit. It also has se.fit here. So if I say pred.newData $se.fit, I get this only. What this actually is the estimated variance of y hat plus the square root of the estimated variance. This is what you would use in a confidence interval for the expected value of y. For a prediction interval, remember what you need. Essentially, for a prediction interval, you would need a 1 plus in that formula. So this is what's actually being calculated. For a prediction interval, though, we wouldn't want 1 plus in there. It does the prediction interval calculations correct. It just gives you a different standard error than what you would expect since we said prediction. I wish they would put what we would want is actually this. I wish they would put that there, but you can actually use this se.fit argument without the interval part. And so then it kind of makes sense. Okay, give me then the standard error for y hat.
This was going to be y hat plus minus y plus.
Excuse me?
You have the estimated variance of y hat plus minus y hat plus.
Oh. Take off. Well, that standard error is hard to calculate. Also here we get the square root of MSE, or what our book would call S. So we use then the exp function here, so I get this on the scale that we want. Here's what we get for y hat. Here's what we get for the prediction interval, kind of y. Okay. Now to do the bootstrap here, of course, I'm going to need to get the mean adjusted modified residuals. So I pull out the hat matrix diagram values. I find the mean adjusted. I find the modified residuals, and then eventually I'll find the mean adjusted modified residuals. To do the bootstrap, of course, I'm going to have to, I can use my boot function. I'm going to construct one of these calc.t-like functions. So I construct a function called calc.t.modBase. There's one particular element in there that it is quite new to us. So here's my calc.t. I pass in my data. Remember what this is going to be, the rj minus r bars. I pass in my indices like usual. These are just, you know, a resample or sampling with replacement of 1 to 60, because I have a sample size of 60. But here's a new part here. I.pret. I purposely used the letter I there because if you remember, what we need are some extra observations that come from our resample to get these epsilon star pluses. So this is going to give me my indices for epsilon star pluses. The boot function will actually pass in some extra stuff. And you'll see the argument that I use in the boot function shortly that gives me these extra resamples. I've got to be careful. I don't want to call them resamples. The extra items that are, I think you know what I mean. So I don't want to call it a resample because when we think of a resample as a sample size n, I don't want to call them extra resample. A resample size 1, or actually I'm going to use a resample size 2. I'm also going to pass in mu.hat. In other words, this is going to be our y hats for I equal 1 to n. I'm going to pass in my x variable. I'm going to pass in my new data that I want to predict at. And then the actual y hats that are calculated for these new data. So these y hats are for these new data. Now, since these observations are actually in the data set itself, I didn't need to do this extra part there, but I'm just trying to write this in a general manner. Okay, so first, I get my epsilon stars. That comes the usual way from these rj minus r bars. Then to get the epsilon star pluses, this is where I grab out those extra rj minus r bars. I find y star in the usual way. Take mu hat, in other words, x prime beta hat, plus my epsilon star. I estimate the model now to this new data, I should say new data, this resampled data. Now remember that this all already is on the log scale here, since I'm just taking mu hat plus epsilon star. So that's why you see a y star here. You don't see a log of y star. I use my predict function just like what I did before when I was working with the observed data. And this is where it gets a little bit complicated here. In order to do the studentized interval, I need, emphasis, I'm going to actually write out I need S sub y, calculated on every single resample, so sy star. Now remember that this is not calculated, S sub y, the sy that I need, is not calculated by the predict function exactly. So what I do is take advantage of, back in the notes where I mentioned this first, take advantage of what we saw up here, where this sy is equal to s squared times 1 plus this other stuff here. What r is giving us automatically is s, and it's taking s times the square root of just this part, the x plus prime, x prime x inverse, x plus part. It's just not including 1. So what can I do? Well, I can get my s squared. I can write number 1 in there. And take that s squared plus s squared times x plus prime, inverse. That's how I'm going to write my code. So, first of all, here's essentially what my MSE is. So I pull out that SE.fit. Oh, excuse me. Let's see. What I'm pulling out here is a vector of length 2. And this is my variance of y hat plus. In other words, s squared, oops, can you read that, or do you need me to rewrite it? I'd be happy to rewrite it. Also, now I can get my MSE. Quickest way to do that, summarize the fit from mod.fit, put that into sum.fit, pull out sigma, square it, that's your MSE, or what our book would call just simply s squared. Then what I do, to find the actual square root of the estimated variance that I need, which would be essentially delta, or variance of delta, let's say. I take the square root of s squared plus sorry, I'm going off camera, plus this guy right. You know, unfortunately, I didn't explain this very well. Are there any questions, at least at this time, or would you like just have to sink it?
Can you repeat me just about delta?
Okay. Remember what delta is essentially. You know, it's a measurement of error. So this is delta. We're actually calculating for a resample, so this gives me the variance of delta star. Then actually what I do here then is actually calculate delta itself.
Can you say why the variance of y hat plus it's a vector of length too?
It comes to, this is where, understanding, what the predict function gives us is very helpful. I'm pulling this out. Because I have two x's that I'm trying to.
Yeah, it's the standard error isn't the same with two different predictions. So you're getting one standard error for each of the different values.
Okay.
This delta has two items in it as well, because I have two x's. So what's returned is a delta that has two items in it, and then the corresponding square root of the estimated variance of delta, essentially, which has two items in it as well. So I returned 4 items overall. And so if I actually try this with some data, just to make sure that it runs, I cannot necessarily replicate exactly the results that were what was observed, because remember that these mean adjusted modified residuals will give you the exact same stuff that you would need to get the original results. I pass in I equal 1 to n. Here's my extra I.pred. I just chose, although I didn't have to do this here, 46 and 47. Observations 46 and 47. And the rest is pretty much self-explanatory. Notice how I get my y hats, or the x pluses, out. Pred.new data, $fit, the first column. Okay, let's do some bootstrapping now. So the data, mean adjusted modified residuals. Everything else is pretty much self-explanatory, or that we've seen before, except for that option m equal 2. That's what tells R do 2 additional items to get from these mean adjusted residuals. So in other words, take another resample of size 2. And what R will do is then for the third thing that it passes to my calc.t function, which I call I.pred, it passes in 2 indices. Now, just as a reminder, we did this back in chapter 2, to help you see what's actually going on. Use the boot function, let's say, for put capital R equal 1, capital R equal 2, and put a print statement here. Say print data, print I.pred, so you can actually see what happens with the boot function. That's how you learn what the boot function is actually doing. So I put the results in boot.res.modbase. Takes us to page 676. Since I need 2 intervals, what I'm going to do is try to combine some of these calculations. So I'm going to use the apply function here. What I want to do is find my quantiles from this delta star distribution. There's actually going to be 2 delta star distributions because I have 2 x's that I'm interested in. So what I'm going to do is pull out of column 1 and column 2 of my boot.res $t. I'm going to pull out of there 2 items. So it's going to be 2 columns. I'm going to apply the quantile function to both columns. So I have margin equal 2 there. And I'm going to try to find a 0.025 and 0.975 quantile. And this is what I get. So for x plus equal to, make sure I get the ordering right here, 52.66. This is for x plus equal to 10.55. My delta star, let's see here, I use 999 resamples times 0.0025 is equal to negative 1.46. Draw that up. That. Delta star 999 times 0.975 is equal to 1.15. Then you could do the same thing for x plus 10.5. So define.
0.16.
I'm sorry, what?
It's 52.16, not 6.
So let's now find the interval on the log scale. What I'm going to do is take my actual y hat plus out of pred.new data, subtract off then the corresponding quantiles that I just calculated. I use the REV function to help me do this. Does anyone remember what the REV function does? Reverse. Because remember, we take y hat plus minus the upper quantile, and y hat plus minus the lower quantile. I use as.numeric there just to remove some unnecessary labels that came along with my pred.new data. And here's my interval, 3.96 to 6.56. On the original data scale, I get 52.56 to 712, 713. Compare that to what we originally had using the t-distribution. Kind of similar. When I had 10.55 for my x plus, these are my results. Again, somewhat similar. What about, yeah.
I have 2 quick questions.
Sure.
For the delta star quantile, how come we're not using 1,000 r plus 1?
Oh, yeah. Sorry. It should be
Oh, okay.
1,000. Now, when I was writing, I was like, is that right? That doesn't seem right. I don't ever remember putting 999 before writing and then subscript before. But yeah, you're right. You should be 1,000.
Another quick question. In the boot function, so we use the m equals 2 kind of in place of the I dot pred. How does calc.t know that m equals 2 is the I pred if we don't actually say I pred?
The boot function passes in as its third thing that it passes to your calc.t, these extra i's.
Okay.
So that's why. So calling it I.pred is not necessary. It's just automatically the third thing goes in there.
Okay. Thank you.
What about a studentized interval? Well, I take my delta star divided by my sy star, which happens to be the third column, when I have my x plus equal to 52.16. I find my corresponding quantiles, and let's just find the lower limit and upper limit, as you would expect. Y hat plus minus then what we would normally calculate for your sy, then times the distributional quantity that comes from the bootstrap. Again, interval of 3.71 to 6.97 for the first x plus, and then for the second x plus as well. These are the intervals overall. These are wider than the basic intervals. Not surprising. So here's just some overall comparisons then on page 678. I compare on the log scale because if we compare on the normal data scale, things get to look a lot more different. But remember, all the calculations are done in the log scale, so this might make sense to do the comparison in the log scale. And so you can see, obviously, the studentized interval is wider than the other ones. I also include for the basic. The authors calculate the interval slightly different than what I did, and I basically ran their corrected program just to illustrate what you would get from it. we can see, the normal base is a little bit shifted down. So this normal base means that regular old t distribution interval assumes normality for your epsilon. It's a little bit shifted down from the other ones. We can look at a distribution of z star as well. I'm just going to do it for the case of x equal 52.16. Now remember, with the normal base interval, your quantile for your t distribution that you would use is essentially -2 to +2 with the corresponding degrees of freedom used. This is what I get for my z star. And so you can see this is where the differences are occurring from above. The distribution is it's not necessarily quite, but it is obviously different. And we could do a plot then of the distribution. Blow this up a little bit here. So this left plot here is all my z stars. I put the blue line is the t distribution. So that again is what's used normally for these intervals. And you can see differences in the distribution. And that's why we're getting different intervals. Okay, we are over by 1 minute. Are there any questions? Okay, so that actually ends Chapter 6 notes, essentially. You're welcome to read the rest of the chapter if you're interested, but you're not responsible for it. And next time we will start then this parallel processing section. As you can see by all my handwriting, I have a lot of notes I took and wrote to myself to help me remember what to say. Anyway, that's it for today.